Thank you so much, Kim. That was really beautiful. And a great note to end up on. I really love that piece. Thanks again. And welcome everybody to the January meeting of Orange County Astronomers. We are in a new year and we're still in our old elections. So if you haven't voted yet, today is your last chance. You still have a chance to vote by computer. You could still get your envelope in the mail if you want to do it the snail mail way. As long as it's postmarked today and gets to Tim, he can count it. And hope you'll participate in our aim at getting good leadership for the club or endorsing the leadership that we have, whichever way you want to look at it. Anyway, I see a number of board members are actually on, and good to see you all, even if only by Zoom. Anyway, without more ado, I will, I think, turn it over to our wonderful panel of announcers, starting with Kyle, because we have a great evening in store, and I know Raisa wants to get to the real meat of the program. So Kyle, take it away.
All right, so we're going to start with the usual website tour. If you come here frequently, you probably know about the website too, but for those who are new, we always like to go over it. So starting on the homepage, right at the beginning, you'll have your information about the next general meeting. If you click on view meeting info, it'll take you to the location with the link, which I assume you all found because you all made it here. Recent articles will be further down. And then at the bottom here, where it says upcoming events, you will see the next 3 upcoming events on the club calendar. If you click view more, it'll take you to the calendar, which I'll show in a moment. The Orange County astronomers are part of Amazon Smile. So if you use Amazon Smile, any purchase you make on Amazon will go, a small percentage of that purchase will go to the club. And then down here where it says buy a shirt, OCA merch you can buy there, such as shirts, etc. And then if you come back up to the calendar, which we'll go to next. Oh, I should make this full screen so you can all see it bigger. There we go. Here on the calendar, you can see all the various upcoming events on the calendar. And then if I hover over one and click on it, it'll give you some information when you hover over it. And then you click on it, it'll take you to a web page where it'll say where it is. Obviously, due to the current situation where online it provides the link, it will put where it is, though, if it's an in-person event when we get back to normal times. Next, I'll go to the special interest groups tab. Cosmic Adventures is going well. If you're interested, you can click on it and see more information about it. And then I'm going to go to the special interest group page. Have all the special interest groups are on here, but we would encourage everyone to join this one on the bottom, the OCA Astronomers group. This is just the club email list, so if you want to stay in the loop about what's going on in the club, you can join that group email list. Then lastly, if you click on contacts, then you will see all the contacts of all the board directors, and then coordinators. Pretty much anyone you would need to contact, you can find on the contact page. Their emails are there, so preferably email them. But if you do need to call, the phone numbers are being answered. So that's it for the website. Now we will go to the presentation for the last part. Here we go. So now for the announcements. As Barbara mentioned, the leadership elections are now in progress. The last night is tonight at midnight is when that electronic voting link will close. So please do participate. These are the candidates running. Even though it is obvious who can win, we do like to have people participate and vote to ensure that people actually support the people who are running the club compared to just, not doing anything because they're the only people running. So please vote as a vote of confidence. All starter parties are on hold due to the ongoing pandemic. Same with in-person special interest group meetings. However, the board meetings and the beginners classes are online. You can see the dates of those there as well as on the calendar. So I'll turn it over to Cecilia and her crew now.
Hello, my name is Panama, and we would like to welcome all new members. We hope you enjoy this fabulous meeting we made for you. Special interest group. It's a small group where people under 18 can see the stars. There are many events, but sadly they are all delayed. For more info, please contact Doug. For the outreach events, they're all online, they're virtual. So we are doing some outreach during school hours now, and mostly at nighttime. So we are looking for people that have the computer set up like that. And thank you so much. If you have anyone that wants to do an event,
It's outreach@ocaastronomers.org, and then I'll be answering those questions or requests. The WAA had finally our meeting for their award for Big Qual, and it was great. It was actually December 30th, and it was a Zoom event, and it went great. So next time we know how to do everything else. So again, if you know Bing, make sure you give him a heart around, round of applause. So, and now a moment with Galileo.
Hello, my name is Galileo, and today is going to be a winning present. And hopefully you see the stars today and the beautiful moon. Present.
All right. Thank you. And then also for the serious astronomer, we're looking for new articles. So we're looking for not just articles, images, observations, etc. So if you have anything you want to put in there, contact Dave Fisher at newsletter@ocaastronomers.org. Members are discouraged from visiting the ANSA site due to the ongoing pandemic. Join us for the Open Spiral Bar, which will be tomorrow night at 10 p.m. It's a social opportunity just to make up for the events that aren't happening with your, people either after the meeting or whenever when you get to socialize. It's to try to replace that social element that isn't there in these virtual meetings, is obviously those who are in the audience can't interact with fellow audience members like you would after a meeting, chatting and whatnot. So go there if you would like to participate in that. And then on tonight's agenda, we have Alex McConaughey from RAS doing the What's Up. And then our main speaker, Dr. Marcel Pawlowski from the Leibniz Institute for Astrophysics, talking about dark matter and the dance of dwarf galaxies. Stay tuned. The What's Up presentation is next. The next meeting is February 12th. Alex, the floor is yours.
Hi, Matt here, and I'll get going. Is everything working okay?
Yes, except we are hearing a ringing sound.
We're hearing the rings.
Do you have an alarm set?
Yep. And I've got these big earphones in so it doesn't come through. But at any rate, let me get going here. Welcome to 2021. Anything besides 2020. This is the first What's Up of the new year, and I am so glad it's not that stinky old 2020 anymore. Come on, let's face it. 2020 was, as Time magazine said right on its cover, the worst year ever. We all fought through a pandemic. Hopefully, we lost nobody we knew to COVID-19, and we survived any infections that we might have had. We should consider ourselves most fortunate if we managed to avoid the infection completely. But no matter what, it was a constant disruption, a constant drag on our ability to hang around each other, to enjoy life to the fullest. Thank goodness for the health professionals, the scientists, the forward-thinking political leaders, and all the others who've gotten through. So far, we've gotten through. And they've shown us that there is a light at the end of the tunnel. 2020 had an election that pitted the forces of evil against the American way. And there was so much division in the country, we couldn't tell which side was which. California, Australia, Brazil all had massive forest fires. We had so many hurricanes, we had to borrow names from the Greek alphabet. Many people lost their jobs. Basketball lived in a bubble. And a shortened baseball season had designated hitters all over the place, and extra innings starting with runners in scoring position. And a night out was running down to In-N-Out to get something in the packaged meal. And I mean, 2020 has likely killed off Wilman Bell. Our life as amateur astronomers will be truly different. all these dismal events are still around us. I mean, I'm sitting here in front of a computer monitor instead of with a donut and coffee and the table in the back of the room at a crowded shopping college auditorium. But it's not 2021. It is 2021 and it's not 2020 anymore. And we're not looking back with 2020 hindsight, but forward to that light at the end of the tunnel. And as with any new year, it's time to make some resolutions and look forward to the new year. I've thought of a number of things I want to do better in the new year, and I hope you have your list. Over the next few minutes, I'm going to tell you about my resolutions to make my hobby life more organized, how I want to make plans and actually follow them along to meet these goals. I hope to expand what I've been seeing and doing and not live in the old ruts of the past. As always, I'm going to make plans to go out and observe and image more. I'll ask you to make your own New Year's resolutions for a better year and for a better you in astronomy. And of course, you should have some non-astronomical goals too. But let's look at what's up for now. Not much is happening observationally in the solar system. A couple of weeks ago, this alignment of Saturn and Jupiter treated us to a really pretty Christmas star. But that pair are setting in the west for us, and we won't get a good look at them for a few months. Mars continues to be visible, as are the outer planets. Mercury and Venus will continue their dance around the sun, with Mercury actually having a very special day on January 24th. Mercury will be about as far away from the sun as it gets, called its greatest elongation. This is the best time to see Mercury. Although Mercury was known to the ancients, and it's easy to spot if you know when and where to look, it's speculated that fewer than 1 in 2,000 people have ever knowingly seen Mercury. It will be on the ecliptic, separated from the sun by about 18 degrees, a little more than the outstretched pinky and index finger at arm's length. You can find the ecliptic by tracing the dying glow of where the sun went down up towards very bright Mars. The planet will be nearly 5 times brighter than the nearby first magnitude star Fomalhaut. Look westward, naked eye or with binoculars, and some 45 to 60 minutes after sunset into the glow of the horizon. If you see a relatively bright star-like object, that's Mercury. You're 1 in the 2,000 people who have ever knowingly seen it. Now remember that Mercury has been studied mostly during the day. It's not up at night since it's always so close to the sun. If you're adventurous, try viewing it or imaging it during the day. Just make sure that the go-to on your scope is calibrated right on, and be very careful. If you're off a bit, you could inadvertently slew past or point to the sun and lose a camera or an eyeball. I've seen all 6 of the traditional planets except Saturn during the day within a couple of hours of noon. 2 of them I've seen naked eye, so it can be done. I'd love to tell you about what is happening about meteor showers and conjunctions and syzygies and visitors from the Oort cloud and all our intrepid astronauts and robot probes heading out into the solar system and beyond. And there'll be a lot of that in 2021, but there isn't much in January. And we should, though, resolve to make ourselves better solar system observers in 2021. Here are some suggestions for what you could do to improve your skills. Go ahead and read them along with them, but a lot of solar system observing can be done from the suburbs. The objects are generally bright. They're visible to the naked eye, many of them. So make a plan or do some serious solar system observing. The Astronomical League offers 2 programs that will definitely enhance your solar system observing. These projects here, the many included in blue here, are included in the offerings in the solar system programs. They will make yourself a better solar system observer in 2021. If our goal is to get organized, make a plan, finish a job, and do something new, we need to have something like this to get us going. There are also things we should be doing in deep space category in 2021 to make ourselves better observers and imagers. Here are some of the showcase objects of January. Some are naked eye, like the 7 Sisters. Others take binoculars or a small telescope, like M38, the open cluster. Others can be hard to find and take official big telescopes. Crab and Thor's helmet are in that category. One's a galaxy. Now, most of the galaxies, the famous galaxies we observe all the time, are above or below the plane of the Milky Way and escape its own stars. This one, however, hides in the dense thickness of the stars in the plane of our Milky Way and making it very hard to find. Some objects, like the California Nebula, are pretty much available only to imagers and those with wide field telescopes in a very dark skies, and then only briefly. But these are the January highlights. If you want an extra challenge this January, try finding the pup in the big dog Canis Majoris. As many of you know, Sirius is the brightest star in our skies besides the sun. It's a double, and the dog star has a little pup hidden in its glare. Well, January is a good time to see that pup since it's at zenith at 10 p.m., prime observing time. In its 50-year elliptical orbit, or how it looks here, the little pup moves from about 8 to about 32 astronomical units from the big star. And as you can see from these dates, we're right about as far away from as it ever gets at about 11 arc seconds. I used this beautiful 10-inch APO refractor by Yuri Petrunin at the Winter Star Party a few years ago to see it. And I think I've seen it with my 15-inch Dob, but I'm not so sure on that. I've heard many reports that under the right condition, a 4-inch refractor will reveal the pup. Here's an image I found on cloudy nights a few weeks ago. Incidentally, it was taken with a cell phone on a 14-inch Dob. As you can see, the star is easy to lose in the glare of the big dog, but it can be seen. Move your scope to Sirius itself, and then move the tube slightly off so that Sirius is just off the field of view to the southwest. The little star you see is just what you're looking for. Once you see it, try moving Sirius itself back into the field of view. Now that you know what you're looking for, you will have your quarry. Now, don't be deceived by other field stars that may be in the field of view. But if we are talking about deep space observing in January, undoubtedly the star of the show is Orion, the mighty hunter. Here he's displayed through the creative genius of Rogelio Bernal Andreu. Notice the various bright areas that draw our interest. Hydrogen gas glows throughout with all sorts of other objects just screaming for attention. But even the most popular deep space targets of them all, M42, magnificent M42, the Orion Nebula, is just a little part of that overall magnificent and wonderful and famous Barnard's 33, the Horsey, is so tiny in comparison, it can hardly be seen. Instead, Barnard's Loop and various other dim gaseous nebulae fill the image. Here's what it might look like in a good but typical amateur shot. I mean, not everybody is Rogelio Andreu. And here are some of the objects of interest in and around the constellation. Betelgeuse is a huge star, could go supernova at any minute, or maybe it already has, the light just hasn't gotten here yet. We have star clusters, stellar nurseries, dark nebula, double stars. It's all happening in Orion. We could spend months here alone, but remember, its time is now. Seeing these planning graphs, it reaches the high point in a given night sometime before midnight, prime viewing time. And in the course of the year, as you can see from this telescopius graph, January is when it's at the highest, and it will be going away. So now is Orion time. Speaking of Orion time, if you're an imager and want to participate in the Astro Imaging Channel's video of Orion's highlights, be sure to send your contribution of something taken in Orion this year, or Orion itself. Just go to the astroimagingchannel.org and Orion time, and you can submit your shot to be included. And for those of you who don't know about the Astro Imaging Channel, allow me to make a shameless plug. We're a friendly YouTube group with more than 10,000 subscribers, some 50 to 100 of whom meet every Sunday night at 6:30. We have more than 300 shows in our video catalog about astro imaging. Feel free to join us in person and ask questions of our presenters every Sunday, or surf at your leisure through the more than 300 presentations we have made through the years about astroimaging. Just Google the Astroimaging channel to find our website and YouTube. But let's get back to the New Year's resolutions. Our overall resolutions are to get organized, make a plan, finish a job, and do something new. Well, here is what that translates to in deep space. See this list of fun things you could be doing? Incidentally, this collection of January objects that form the background of this slide comes from the first two items on this list of resolutions. I have to prepare a monthly observing list, or imaging list in my case, and go out and capture it. I prepared my list by studying books like these: Ruben Kier's 100 Best Astrophotography Targets and Mike Bakich's 1001 Celestial Wonders to See Before You Die. These are two good books for those who want to make an observing list. And there are websites and even programs in most go-to scope controllers that can suggest what to look for on any given night. One of the things I like about the layouts in this book, though, is that they're organized by month and day. They contain text descriptions and images, often full color, of the objects. This enables one to organize the lists by what they see in these books. Here's another cool way to stick to your resolution to become a better deep space observer. It really helps to plan your observations. It's a free website called telescopius.com. You can tell it when and where you are and when you're planning on observing. It will suggest sample objects and show how high in the sky they are. That's this area right in through here. And give you sample images of what you might see. If you tell it what particular object you look for and tell it what kind of telescope and eyepiece you have, it can even frame it as you would in your eyepiece or your imager. With tools like these, you can make better plans for what you're going to be doing tonight with your telescopes, and you won't be wasting such time just wandering around. But let's get back to our New Year's resolutions related to deep space. Again, these are only ideas. You will find many more by reading Sky and Tell or listening to your astro buddies. And of course, the Astronomical League observing programs have lots more ideas. But the important thing is that you decide on a few of them and complete the project. The important thing is that you make and keep your resolutions. 2020 is over and gone. We can start coming out of that cave. We can begin to look up. After all, sitting alone in the desert with your scope easily conforms to social distancing requirements. Let's make a resolution to get with it. I have my resolutions and I've already started getting on them. Go get yours and move into this new year with a new vigor. Stinky old 2020 is over and it's a new year. Thank you.
Thank you very much, Alex. Very entertaining and informative. I'm going to look at the horsey tonight, hopefully. So I would like to take this opportunity to welcome everybody to the first general meeting of the Orange County astronomers in the year 2021 on January 8th. This is Reza, the vice president of the club. Before introducing our speaker for the night, I would like to remind you that you can use Zoom's raise hand function to applaud the speaker, chat to send us any comments you may have, and a Q&A during and after the talk to ask your questions from the speaker. The research of our tonight's speaker is situated at the intersection of observations and cosmological simulations, and he is most interested in testing our cosmological knowledge and our understanding of the properties and dynamics of dwarf galaxies with observations of nearby systems of satellite galaxies. He has received his PhD in 2013 from University of Bonn and has held the postdoctoral position at Case Western Reserve University in Cleveland, Ohio. In 2016, he was awarded a NASA Hubble Fellowship to work at the University of California, Irvine. At the end of 2018, he moved back to Germany to his current position as Schwarzschild Fellow at the Leibniz Institute for Astrophysics in Potsdam. He has just won a major grant that will allow him to start a research group at AIP next summer, and the topic of his project is closely aligned to what we will hear him talk about tonight. please join me by raising your hand virtually in welcoming Dr. Marcel Pawlowski. Marcel.
Hi. Yeah, thank you for having me. It's quite a pleasure to at least virtually return to Orange County. Let me know if anything doesn't work. I'll start sharing my screen now. Always a bit difficult with lacking feedback in virtual talks, but I hope this works.
Okay, we have you all clear and good.
Right.
I see there's an animation going, but nothing is okay. Started moving again. All good.
Yeah, it's
floor
just
is all
background
yours.
so far. Okay, thank you. So yeah, I'll talk about dark matter and the dance of dwarf galaxies. It's kind of main theme of my research for the past 10 years or so. Let's start with something simple. Galaxies. We all know what galaxies look like. This is our closest massive neighbor galaxy, the Andromeda Galaxy. So it's a big, nice spiral. And that's not the only type of galaxies we have. Especially these big galaxies are surrounded by smaller ones, so-called dwarf galaxies. You can see two here. There's one up there and another one down here. And further out in the field, the one Andromeda, there are many more, similar for the Milky Way. One of those satellite galaxies, or as they are also called when they are orbiting around a host, is the Triangulum Galaxy. It's another spiral galaxy. It's the most massive satellite of Andromeda. And as you can see, it has also a really nice, beautiful spiral structure. We know that spiral galaxies rotate because we can measure the speed of gas or stars in them. So one example here is this is the deuterohydrogen velocity field in this galaxy. And when we measure this, we can look at the relative speed of different sections in this galaxy. We know that some parts are approaching us and some parts are receding from us. It's essentially the Doppler effect. You can look at spectral lines in a galaxy, and when they are shifted, it tells you that they're either moving towards you or away from you. And in this case, if you map this, you see that one side is approaching, it's blue shifted, the other one is receding from you, it's red shifted. So this galaxy seems to be rotating. From this rotation, you can derive the dynamics. So what we see here is an animation. Of course, not a real observation. We don't have the time resolution. Well, we don't live long enough to see any real movement in a galaxy in a sense like this. But this is our expectation of what the rotating galaxy should look like if you could watch it for millions and millions of years. So we would expect that it's moving really fast in the inside, and then because most of the mass is kind of in the center of a galaxy, most of the stars in the center, as you can see, it's brightest there, then the speed should drop off. So this is shown down here in what's so-called galactic rotation curve. So it's a curve plotting the rotation velocity on the vertical axis against the distance on the horizontal axis. And we would expect that it's what we call a Keplerian drop-off to larger distances. It's like in the solar system, we have a massive sun in the center, and further out, the planets don't really contribute much mass, so their rotational speed around the sun is getting smaller and smaller the further out they are. So this is what we would expect. Now, from measurements like these, we can construct observed rotation curves, and they are actually looking more like this. They are flat out to large distances, which means that the rotational speed is more or less constant at larger distances, even though we would expect it to drop off. And that is, one explanation of that is the missing mass in this galaxy. If you don't assume that it's just the stars which are contributing to this rotation, but there's additional mass in the galaxy, then you could account for this. And you can turn this around by saying, okay, we need to account for this somehow because it's our observation. So how do we have to distribute additional mass to come up with this? And that introduces kind of a somewhat exotic concept. So there are two possibilities to explain this flat rotation curve feature. So we know that the galaxy consists of stars, and we know that there's gas in galaxies as well. So we can measure that. We can measure how much of that is in a given galaxy. And then we can, well, calculate a star at a certain radius with a certain measured velocity. We know it should be on a stable orbit around the host. The question is it? So if we just assume, sum up the stars and gas we know of, and assume Newtonian gravity, so it's just your standard gravity working in the solar system on Earth, that's what we're used to, right? Then this galaxy would not be bound. It would just fly apart in a sense. So to account for that, as I said, we can add additional mass. It's so-called dark matter. In a sense, we increase the mass of the galaxy by adding stuff. This dark matter is thought to be a new elementary particle. By definition, doesn't interact in any electromagnetic way, so we cannot see it. We cannot see its shadow. It's not absorbing light and it's not emitting light. So it's in a sense a necessary condition, because otherwise we would have seen it, right? So by definition, we can't see it with a telescope, but we can see its effect. Its effect is that it adds mass to the galaxy, and that then accounts for the rotation. And that keeps galaxies nice and stable. So for a given rotation curve, you can infer how much dark matter there is in a galaxy, and that kind of saves the day. However, because we can't see it, and detection experiments looking for this new particle have come up empty-handed so far, there's an alternative explanation of this. So forget about dark matter for a moment. The other possibility is, well, we assume we have, well, we know that we have stars and gas in the galaxy, and we assume a certain law of gravity. This law of gravity is really well tested in the solar system, really well tested on Earth, but that's, astronomically speaking, a high acceleration regime. So they are relatively strong forces. If you go to a galaxy, which is extremely vast, and the distances involved are extreme, then we don't really have a good test of this gravitational model. And there's the possibility that you can modify the laws of gravity on these scales. And in that sense, you would calculate a different force from the given existing mass, and that could stabilize your galaxy. So there are two possibilities to explain rotating galaxies. One is you add an exotic particle, dark matter. And the alternative is, yeah, you have to come up with a kind of exotic gravitational model. So either way, there's something new, and it's of course exciting for scientists, but we kind of want to figure out which one is it, right? So, so far, astronomy has mostly focused on the first possibility, which is dark matter. One reason is it's super easy to calculate. Another is it can match a lot more observations than just rotating galaxies. So over the last decades, we've built up a so-called standard model of cosmology, which tells us what the universe is made out of. So there are so-called baryons, which is kind of ordinary matter. That's what we are, what everything on Earth is. As we can see, this is only a few percent. So we are just a tiny fraction of the total energy density in the universe. There's dark energy, which I will not go into this in this talk, because it's really acting on larger scales than the individual galaxies we're looking at. But that's actually dominating the energy budget of the universe today. And then there's this dark matter, which is about 5 to 6 times more. There's 5 to 6 times more dark matter in the universe than in baryons, than in you and me. And it's also kind of a misnomer. We should maybe better call it transparent matter, because it's not dark. It doesn't cast shadows or anything. It's really just, we can't see it. It passes through us. There's no interaction with light by definition. So the idea of my research now is let's test this dark matter model by comparing its predictions with the distribution and motion of observed satellite galaxies. So how do we get predictions in this dark matter model? That's one of the big successes of the model, is that we can run computer simulations of the universe. We basically start out very early, just after the Big Bang, with an almost homogeneous distribution of matter. So we put that into a computer, and then under the laws of gravity, we let it evolve and see what happens. So there are little tiny fluctuations in the initial density field, and those grow into bigger and bigger overdensities with time as gravity in an overdense region collapses the region, and that gives you a higher overdensity that attracts more matter, and that way things grow. And then you will see that little blobs of dark matter will form together and build bigger and bigger blobs, which is what astronomers mean with a hierarchical formation scenario for galaxies. So we start out with small galaxies and build them up into bigger ones. So this down here is an animation. I'll start that in a moment. So starting very early in the universe, this is 13.6 giga-years ago. And yeah, you can see it's mostly blue right now. So it's kind of relatively homogeneous, but there are small fluctuations already. And when we start this, we see that relatively quickly, with stronger overdensity forms in the center. There are these filamentary structures forming, kind of a cosmic web along which additional galaxies fall in. And then in the center, so-called dark matter halo forms, which is a big blob of dark matter. And this one in particular is well, comparable to what we expect the Milky Way's dark matter halo to look like. And then you see all these little blobs. As I said, they are kind of little dark matter halos, little blobs of dark matter, which merge together. And we expect those to host smaller galaxies. And that naturally explains why we have galaxies like the Milky Way surrounded by smaller satellite galaxies. And this also has a strong prediction for the dance of these dwarf galaxies around the host. We've seen, I can maybe go back a little bit. We've seen they are coming in from all kinds of directions and they are moving around rather chaotically. And we see that, yeah, they are more or less evenly distributed around the central galaxy here. So this dance looks a bit like this. It's kind of chaotic. It's just drawing aptly named Dance in a Madhouse. So they have fun, but they are kind of not really following any specific choreography. They are just running around like crazy. You could also compare that to a modern, I don't know, metal concert where people just bang into each other all the time, which of course, in the current times, we don't really celebrate anymore. So that's kind of the prediction. Our model predicts satellite galaxies to move around like crazy. Now, what do we observe? As I showed in the beginning, we have the Andromeda Galaxy. It's our nearest neighbor galaxy. And in this picture, we already see two satellites, M32 and M110 down here. Some of you might have owned Mac computers in the past, and this is also kind of a warning I have to say here. Don't trust big tech companies in your astronomy because they make galaxies vanish. They had this nice galaxy, the Andromeda Galaxy, as one of their default wallpaper backgrounds a while ago for one of their operating systems. And as you can see, they didn't like this galaxy, so they just made it go away. So yeah, the Empire and Star Wars blew up a star. Apple removed the whole galaxy. Anyway, I'm using Apple computers too, so kind of it's my fault as well. So this is as I said, the Triangulum Galaxy, M33 is a bit smaller than, well, quite a bit smaller than Andromeda, but still a massive galaxy. And let's look at smaller and smaller galaxies now. This is the Large Magellanic Cloud. It's a galaxy around the Milky Way. The most massive satellite of the Milky Way. It's, as you can see, has a strong bar, and then there are some nice star-forming regions in there. And there are lots and lots of stars, but this is the most massive satellite. There are fainter satellites, Fornax, for example. You still see a strong overdensity of stars here, but you also see here kind of it goes away, and at some point there's an end of this galaxy, of course, and then you just see here the foreground stars of the Milky Way surrounding it. And as we go to fainter galaxies, it becomes more and more difficult to spot them, right? So this is Carina. It's still one of the more massive satellite galaxies of the Milky Way, but it's already kind of difficult to say where it is exactly in the picture. So it's kind of here, this overdensity of stars. If you look at the corners, there are less stars than the center. And yeah, you can go on and on. So this is a series of 9 dwarf galaxies around the Milky Way, starting with the LMC, which is most massive, and then going down in mass. So you see that Andromeda, the LMC has about 3 times 10 to the 9 solar masses in stars. So it has billions of stars. Fornex has about 100 times less. And then as you go down to like Draco has only a few 100,000 solar masses in stars. And then the faintest satellite galaxies of the Milky Way consists of only a few thousand stars. So this is a huge range in masses. And this picture is a bit misleading because the sizes involved are also very different. So if you rescale every picture to the same scale, this is what it looks like. So we have kind of massive satellite galaxies, but then the faintest one are really, really tiny and small and kind of very difficult to discover. But due to digital sky surveys, which kind of scan huge portions of the sky digitally and then identify all the stars, we can identify where there are these little tiny overdensities at given distances. And that has exploded our knowledge of satellite galaxies around the Milky Way. So astronomy always has kind of a nice connection to history and how things evolved, because we are still, well, for one, we make a lot of discoveries, and so there's a lot of change. At the same time, we have a kind of long history as a science. So in the local group consists of the Milky Way galaxy, our neighboring Andromeda galaxy, and all the little satellite dwarf galaxies around them. We didn't know too much about this, let's say 70 years ago. I came across this really nice Life magazine in an antique store sometime in Virginia when I was visiting a friend there. And I immediately had to get it, of course, because of this really nice article, which was about, well, what we knew about galaxies and cosmology back then. And there's this picture here. It's what we knew about the local group when this was published in 54. So we knew that there's the Milky Way galaxy. We knew that there's the Andromeda galaxy. We knew of a few star clusters around them. We knew of the magnetic clouds. There were actually some galaxies in this picture which we now know are not even part of the local group because they are way further away. But that was basically it. There's M33 up there. And yeah, we didn't really know too many satellite galaxies of either of these two massive systems in the local group. Now, this has changed. By now, we know hundreds of dwarf galaxies. There are at least 50 or 60 around the Milky Way, which we know of, and we expect a huge number more. And most of these discoveries were actually made just in the last 15 years or so due to these digital sky surveys. So this is an animation I made a little while ago. So what we see here is in the center, this is a schematic orientation of the Milky Way disk. So this would be the disk of the Milky Way. In the very center, there's a little dot, that's the position of the sun. It will move. That's not because the Milky Way is rotating, because this starts 100 years ago and we wouldn't see any visible motion in that time scale. It's actually just the animation rotating around the Milky Way, or the Milky Way rotating. So to give us an idea of the 3D distribution. And this starts in the year 1920, which is when we knew of, well, large and the small magnetic clouds. That were all the satellite galaxies we knew of. And that's also because we can see those with the naked eye if we're in the southern hemisphere. Now, when we start this, as I said, that's the Milky Way, we are there. And yeah, those are the two most prominent satellite galaxies. We can start this movie and then we see that with time, a few galaxies were discovered. The so-called classical satellite galaxies are the brightest ones. They've been discovered over kind of first part of the century. And then it took until the digital revolution that there really was an explosion of additional discoveries. So at first there was a so-called Sloan digital sky survey, which covered the northern hemisphere here mostly. That's the wet points. And then in recent years, there were a number of different surveys which kind of filled up our knowledge in the south. So we have a lot of data to play with now, and we can also see that they are not completely randomly distributed. So there's some preference there. So again, to remind you, my idea is to test this dark matter model by comparing its predictions as derived from computer simulations with the distribution and motion of observed satellite galaxies. So what do we expect them to look like again? Well, they should come in from all sides and directions. They should be distributed randomly around the Milky Way, and they should move in basically completely random directions, with a little bit of preference from these large-scale filaments, of course. But once they are close to the galaxy, which is kind of indicated by this circle, is kind of this sphere of influence of the Milky Way in the simulation, there they should really move in all kinds of directions and forms. So this is the expectation. What do we actually see? Well, we see more structure than expected. So this is a plot from a figure I published quite a while ago. It's a view from outside the Milky Way, and it indicates the positions of all the known and suspected satellite galaxies. So the Milky Way disk would be seen edge on. So you have the disk of the Milky Way, and you look at it from the really narrow side. There are regions in the sky where we can't discover any satellite galaxies, because if you look through the Milky Way disk, it's just completely full of stars and dust. So you can imagine that if you want to discover a satellite galaxy consisting of 1,000 stars, it's impossible in that region where there are billions and billions of stars of the Milky Way in the foreground. But outside of that, in the northern and the southern hemispheres, we can actually discover things. And what we see here is they are distributed also in a kind of a narrow planar distribution, which we also see edge on in this view. So there are huge patches of the sky which have been surveyed, where we have observations, but we haven't found any satellite galaxies. So here on the corners, they could be filled, but they aren't. Now, okay, we know that the satellite galaxies are not completely randomly distributed. This is unlikely if you compare it to the simulation, but it could still, in principle, be a chance alignment. They could still move outside of this direction here. But they could also rotate in that plane. So in a sense, the question is, do they dance around in a common circle? Is that really kind of a choreography they are following? Or is this more like the picture I showed before, where they are just having fun and bumping into each other all the time? To settle that, we need velocities, and we don't only need the line of sight velocities, which are, as I said in the beginning, relatively easy to measure with this spectroscopic redshift or blue shift. But we need to know, where do the satellite galaxies move on the sky? That's conceptually also very easy to measure. What we see here is kind of the concept of it. You sit on Earth, you take a picture of the sky, you want to know how fast is the star moving on the sky. So it's kind of its angular speed on the sky. So you take a picture of the star in front of background stars. There are always background stars or background galaxies in your field of view if it's big enough. And then you wait a few years, and then you take another picture. In the meantime, the star has moved, of course. And comparing these two pictures, you can say, okay, this is how fast the star is moving. This is actually possible to do. This is a pair of stars which are, I think, the fastest as seen from Earth. And you can actually see these are different observations, starting in 2012 and going up to 2016. You can actually see how these two stars move relative to the background. So this works in a sense, and it's, of course, a really simple technique. You could do it with your own camera in principle. Then the good news is these satellite galaxies are moving really fast, hundreds of kilometers per second. Yeah, sorry, I'm a European. You can change that to miles per hour, per second, of course. They are moving really fast. The problem is they are really far away as well. So the angular speed on the sky is tiny. Well, these are huge numbers and they're not really intuitive. So let me give you a comparison. Imagine you're sitting on Earth and you're watching an astronaut on the moon. It's kind of, the measurement you have to make is how fast is this astronaut's hair growing on the moon while you sit on Earth. That's the angular speed with which these satellite galaxies move. So it's an extremely precise measurement you need to make, and it's best made from space because you don't have the atmospheric distortions of the Earth in the way, in a sense. And nowadays it is possible using, for example, the Hubble Space Telescope, which is a super precise instrument for this, or the dedicated Gaia mission by the ESA, which is also dedicated to measuring exactly these motions of stars relative to each other on the sky. Now, if you have a satellite galaxy, you identify all the stars which belong to it, and then you look at how are they moving on average. So you get additional precision by averaging over many stars, which is of course easier if you have a massive satellite galaxy. If you have a galaxy which only has a few hundred stars, then the precision is lower, but it is all measurable nowadays. And yeah, what comes out of that? So this is a representation of the sky around the Earth, or sky view. In a sense, it's like a map. It's like a map of Earth, but looking up instead of down. It's oriented such that the Milky Way disk is here along the equator. So this is the Milky Way. It's inverted, so all the bright stars are dark here, because that allows me to nicely plot the positions of the known satellite galaxies on it. So these little black dots as well as the white dots are known satellite galaxies of the Milky Way. And we can see that they are preferentially oriented more or less along this band on the sky. So in 3D, they are kind of in a flattened distribution. If you're sitting in the Milky Way as we do and look at the whole sky, this flattened distribution translates into kind of a wing around us. There's some scatter because this structure has a certain width. But yeah, there's definitely a preference for satellite galaxies to be distributed along this direction. And then you see this big feature down here, this dark patch, that's the so-called Magellanic Stream. It's a gas stream trailing behind the Magellanic Clouds. So you have the LMC, the Large Magellanic Cloud, the Small Magellanic Cloud, these two satellite galaxies we know since ancient times. And they are kind of trailing behind them this gas stream as they orbit around the Milky Way. So it already tells us that these two galaxies are kind of moving along this direction as well, which would fit with an orbit along the plane of satellites. Now, the expectation from our cosmological simulations is, okay, even if the satellite galaxies are distributed not randomly, but in a kind of flattened, planar oriented way, then at least the motions of them should be outside of this plane. So they should have velocity vectors in all kinds of directions in this plot. Now, what do we actually observe? That's the red points here. So there's a lot more ordered motion than expected. We see these two galaxies are moving in this direction. You have one here, one here. You have the Magellanic Clouds moving in this direction. And this one here, they are also moving in that direction. So Sagittarius, which is this one, is outside of the plane, so it doesn't participate in any of that. But for the others, I think 7 to 8 out of 10 are moving in a coherent way along this orientation of their positions. So it looks like it's an ordered motion defined by where they are. This is kind of the, I think, most sciencey plot I'll show. Bear with me for a moment. On the left, again, we have the orientation of the positions of known satellite galaxies, and we can quantify that by, say, measuring the thickness or the axis ratio of this distribution. How flattened is it? And we can measure how well do the satellite galaxies orbit in the same direction. So are they up here? This would show us they are completely randomly moving. And this down here means they are all moving in pretty much the same direction. And then we can compare that to a lot of analogs of the Milky Way in those cosmological simulations. So these simulations, of course, don't just form one Milky Way. What we simulate is kind of a whole section of the universe where there are hundreds to thousands of galaxies which are like the Milky Way. And then we look at all of these and we measure how are the satellites distributed in them and how well do they follow a coherent choreography in their dance. And what we measure is kind of this point down here. So it's thin, so on the left, on the horizontal axis, and it's very coherent. So the satellite galaxies are moving together in a common direction, which means that we are relatively far down here. And with more recent measurements, this point actually shifts further down. And this is what we expect from the simulations. So these contours here, as well as all these little points, indicate where we expect a given satellite system in a simulation to sit. You can see that you're outside of this whole cloud of points. So less than 1 in 1,000 galaxies in our simulations host something which is as extreme as the structure we observe around our own Milky Way. So we just look at one system, which is the one we have most nearby, and it should happen only 1 in 1,000 times. That is a problem. It means that the Milky Way is either super special or the model predictions are wrong. That would imply that probably the model itself has some issues. So this is a problem for our standard model of cosmology, but it is still just one example, right? It's just the Milky Way. Maybe the Milky Way is special. Everybody wants to be special. Maybe we are because we live in the Milky Way. So is the Milky Way an exception? Actually, no. What we see here is, again, the Andromeda Galaxy. We just go to our nearest neighbor in a sense. And what we can do is look at the distribution of stars around Andromeda. So this is an animation by the PANDAS team. So PANDAS is a survey looking at this region you can maybe make out here around the Andromeda Galaxy. There's a big volume around Andromeda, which has been surveyed in really deep observations, looking for all the stars they could find and looking at overdensities among those stars. And that way they identified about 30 satellite galaxies of Andromeda in a homogeneous way. So that allows us to do nice comparisons and make appropriate statistics of what's happening in the satellite galaxy system of Andromeda. So what we do now is we kind of fly towards Andromeda in this animation. So you see all these foreground stars belonging to the Milky Way kind of moving past us. Many of the stars in this region here are also Milky Way foreground stars because they observe further down, a bit further away in a sense. And then as we get towards Andromeda, we can look at what satellite galaxies did they find in their survey. So this is Andromeda, and then enhance the contrast, and you see these overdensities here, all these little blobs, little points. And then there are also stars, stellar streams, and features like loops. But we identify these satellite galaxies here, and they are highlighted now, and that's the distribution. And when they did that, that's work by Ibata and collaborators, they identify that half of them, the wet ones here, are in a really narrow distribution, right? And that by itself is quite unlikely, but they could do something else. We see this distribution essentially edge on from the Milky Way, and then we can look at the line of sight velocities, which satellite galaxies are moving towards us and which are moving away that belong to this spatial plane. And if you do that, I think that should happen about now, you see that, well, the southern ones are moving away from us, the northern ones moving towards us, the other ones are moving away from us. So this is like a rotating plane of satellite galaxies. So it's very similar to what we see around the Milky Way. So we can also look at this in a more schematic view. This is just the whole local group. We have the Milky Way oriented like this here, essentially edge on, and the Andromeda Galaxy down here. It's somewhat inclined. And then all the points are the known satellite galaxies. And well, we know that there's a flattened distribution around the Milky Way indicated by the blue circles, and there's a similar distribution around Andromeda indicated by the red circles. And they both actually rotate more or less in the same sense. So it looks like the Milky Way itself isn't special. So we have two examples now of such flattened satellite galaxy distributions. And if we compare Andromeda's distribution to cosmological simulations, they are also in tension with it. So that's also not expected. But these two galaxies are close neighbors, right? Maybe this local group is just special. So what about galaxies further out? That's something we asked ourselves a few years ago. And well, we got data for one specific system, which is the Centaurus A galaxy. So this is Centaurus A and some surrounding structures. You see it's different from the Milky Way and Andromeda in the sense that it's not a nice spiral disk galaxy. It's more massive, and it's an elliptical galaxy. So it's kind of more a blob of stars, and then it has this nice dust lane in the center. Now we looked at the satellite distribution around it, and well, we got really exciting results, which made us end up on the cover of the Science magazine, which is really nice. They of course plotted the host galaxy, even though it's basically just the origin of our coordinate system. We don't really care that much about the host. We want to look at all the satellites around it. But still, we don't complain. So what has been known before we did this study is that if you look at the spatial distribution of satellite galaxies, I want to about Centaurus A again, there might be two planes. So you could say that maybe this here is a planar distribution, then offset from that there's a second one. So our research was initially focusing on discovering additional satellite galaxies and looking at their distribution, and we found evidence that it's maybe more one wider distribution of satellite galaxies around the host. But what's again really interesting is how do they move? And it turns out, yes, this is essentially again a flattened distribution, a plane of satellite galaxies that seems to be rotating. So this is a 3D kind of animation of the distribution of satellites around Centaurus A. So Centaurus A is the big black blob in the center. And this line here is our line of sight. So the Milky Way sits at the end of this line, way further out, of course. So from us, we see this flattened distribution. And then if you turn it around, it's really just like a plane. And for 16 galaxies, we knew satellite velocities, line of sight velocities. So again, they are pointing towards our direction or away from us. And again, you can see that there's a preference for them to rotate in a common sense. This half here is blue shifted, so it's moving towards us, and the red shifted part on the other side is moving away from us. And that's again, this signal is aligned with the spatial distribution. So it again looks like it's a rotating plane of satellite galaxies. So we have 3 systems for which we looked at that. And in all 3 of them, we find this strange feature, which is not expected from our models. So this sums it up, right? We have such a feature in the Milky Way. Again, this is a plot from outside of the Milky Way. Milky Way is seen edge on in the center, little tiny line here. And well, if we would see the Milky Way from outside, we would see that this part here is red shifted, so moving away from us, and this part here is blue shifted. These galaxies are moving towards us. We also know that they are staying in this plane preferentially. For Andromeda, we know that this southern part here is blue shifted, so it's moving towards us, whereas the red shifted northern part is moving away from us. We don't really know about their motion on the sky, so they could still have motion outside of this plane, except that there was a recent paper which looked at these 2 galaxies specifically and found their 3D motion, and that is in nice agreement with actually moving along this plane. So it looks like there's also some evidence now that this is also a rotating plane, just like the Milky Way. And then for Centaurus A, we found that 14 out of 16 galaxies follow a coherent movement pattern around the host. And we just yesterday, I think it was published, a new study we made with it, where we obtained additional velocity information for satellite galaxies. And picture didn't change much. With now 28 satellite galaxies, 21 follow the same coherent pattern. So there are a few exceptions, but if you compare that to cosmological simulations, these predictions based on the dark matter model, you in kind of every case see that these structures should happen in 1 of 1,000 galaxies, yet we found them in 3 out of 3. Okay, so that's a major problem, right? It's not clear how to actually explain that. So any ideas what we could do? How can we understand this? Is it really a problem of the cosmological model, or is it more a problem of how we come up with the predictions of the model? So could the simulations be wrong, for example? So when we published this Centaurus A study in Science, there were some interviews performed by journalists, also of colleagues of us who don't really work with us. And one of them is Bridget Falk. She back then tweeted this about an article where she was interviewed for, saying that, yeah, the universe is pretty fucking weird and complicated and science is hard. And yeah, why are satellite galaxies co-rotating planes? The answer might surprise you. And then her answer was, spoiler alert, who the bleep knows? We don't know. We don't really know what is happening. We have a bunch of ideas, and then yeah, give us some money to research it, and we'll stop shouting. So my reaction to that was, yeah, well, I keep getting asked this question, what does explain these observations? And I don't really know. But what we also know, this is another researcher from Australia is chiming in, saying that, yeah, we know that lambda CDM, this dark matter standard cosmological model, that's not really the answer. In this model, it doesn't seem to work. So we really have to work on what's going on. And this is Oliver Müller, the lead author and close collaborator of mine, saying, what's going on? Why are you all shouting? I can't even hear you. Right? So let's just focus on one possible explanation, which is kind of the most extreme and exotic one, but maybe also the most exciting possibility that might come out of this line of research. So it's a effect called tidal dwarf galaxies. So in a sense, if two galaxies love each other very, very much, it's related to tides. We know that on Earth, you have an ocean nearby. I don't anymore. It's kind of one of the big things I miss about OC, except for the weather and the light and the food. Well, so we have, of course, we have the Earth and we have the Moon and we have oceans on Earth. And as the Moon moves around the Earth and the Earth moves around the Sun, we know that we have high and low tides. So in a sense, the Moon is tugging on the water on Earth. Whereas, of course, on the other side of Earth, there's also kind of a centrifugal force, which also causes a high tide. Now, this changes the ocean level by a few meters, maybe. As many things, it's much more violent when you go to astronomical scales. If you have two galaxies coming close together, these tides can be a lot more spectacular. So this is an animation of a simulation of two galaxies, and then it blends over to observations from time to time. It's a really nice way of illustrating this. So we have two disk galaxies which come together now, and they start to collide and interact with each other. So their mutual gravity starts to rip each other apart. So we can see that, yeah, they're still kind of recognizable as disky galaxies, but now they start to deform. And there are these long tidal tails evolving. So yeah, these tails here is essentially what the high tide is on Earth, but much, much, much more violent. So there are stars and gas whipped out of the galaxy and thrown into intergalactic space to really large distances compared to the two galaxies. And yeah, this is just a computer simulation, but we can see that it matches nicely with all these little observations that have been performed of similar systems. You just have to look at it from different angles, and kind of one model can unify all these different interactions. What you also see is that there are these little overdensities along the tails sometimes, and there's some star formation here in the observations going on. Come to that in a second. But yeah, in the end, these two galaxies might merge, form one big galaxy. Often such a merger results in the formation of an elliptical galaxy that would fit nicely with the Centaurus A galaxy, for example, which is a big, massive elliptical galaxy. So we know it must have had a major merger in the past. And yeah, there's another animation of similar simulation where you see that, okay, we form this tidal tail here, and then you see these little blobs like beads on a string. And these are new stellar systems. So they are little satellite dwarf galaxies forming out of the material whipped out of the host galaxy. So this is kind of a way of forming second generation galaxies, little baby galaxies. When these two galaxies love each other very much and they come together, they form little dwarf galaxies. So the really interesting part about that is, of course, these little dwarf galaxies form along a tidal tail. So if you don't trust simulations, you can also look at observations. This is the Tadpole galaxy interacting with the galaxy, which is kind of right behind this disk here. And there's a nice, long, beautiful tidal tail going out, stretching out of the picture here. And you see these star forming regions, these bright blue regions. That's where the young stars are forming, young, really hot, bright stars. And they are forming along this tidal tail. And this tidal tail, as we saw in the animations, is moving across the sky in a coherent manner. So this can nicely explain the observation of satellite galaxies moving in a coherent way in the same direction around the host galaxy. Now, the problem with this explanation is that these little galaxies, they form out of the disk material of a galaxy, right? We saw in the animation of the cosmological simulation where all the dark matter comes together and forms a big blob. That's really just a big blob, right? So the dark matter should move around the galaxy in all kinds of ways, be relatively diffusely distributed, and it wouldn't participate in the formation of this really narrow tidal tail feature. So it wouldn't participate in the formation of these little tidal dwarf galaxies either. So these tidal dwarf galaxies that form in those collisions, they should be free of dark matter. They shouldn't contain any dark matter. Yet, for the satellite galaxies we observe in the local group, so on the Milky Way and Andromeda, we know that they have their stars internally move faster than expected, right? For example, with M33, we look at the rotation curve and we see that it's flat, and well, we can explain that with dark matter. But if these galaxies wouldn't contain dark matter because they are tidal dwarf galaxies, that wouldn't match, right? Except, of course, you go back to the feature of, well, not explaining everything with dark matter, but with modified gravity. And that's why the scenario of explaining these satellite galaxy planes, these coherent motions, this choreography of satellite galaxies, if you explain that with tidal dwarf galaxies, you kind of have to end up saying that maybe we need to switch to a modified gravity approach instead of the dark matter model of the universe, which is kind of a really big step then. So this is what I just said. This is another galaxy where you see this beats on a string feature happening, all these little over densities along the tidal tail. I, in a sense, don't like this galaxy because its nickname is the dentist chair galaxy. As you can imagine, you can sit here and you have your feet here and then bad things happen. At least in space, you can't hear any sound, but yeah, it's kind of unsettling image. Don't know who came up with that name, but unfortunately, it's fitting with the features. Okay, so yeah, just to sum up, tidal dwarf galaxies, they move in coherent ways. We know that they form from observations, and we can model this in the computer, and they nicely explain the features, but they imply that, yeah, dark matter doesn't seem to work. So if you want to explain what we see around the Milky Way, Andromeda, and Centaurus A with tidal dwarf galaxies, we are kind of forced to abandon a very successful cosmological model, which is not something we want to easily do, of course. So that's one of the reasons why yeah, this is a big puzzle, and we don't really know yet what the answer is to this challenge of, yeah, coherently orbiting, coherently dancing satellite galaxies. Yeah, remember, there are these two possibilities, dark matter or modified gravity, and this scenario at least points more to the modified gravity approach. So brings me to the end of the talk. To sum up, satellite galaxies are moving in a much more ordered way than expected. So basically dancing around in circles instead of, yeah, just running around in a chaotic way and yeah, bumping into each other all the time. In cosmological simulations, dark matter kind of forms these structures over time and predicts that satellite galaxies should move rather randomly and be distributed all around the host, like here. You can see that they are everywhere, right? And this would be the center of the Milky Way, and all the satellite galaxies around it would, yeah, not really follow these strong features we've observed. Which, yeah, this is what we've observed. Milky Way satellite galaxies are preferentially orbiting in a common sense along a common plane around the Milky Way, and something similar seems to be happening for our nearest neighbor galaxies, which doesn't really agree with our expectations. Tidal dwarf galaxies might explain this. So they might, tidal dwarf galaxies actually really nicely explain the distribution, but then there's the additional problem that they should be free of dark matter. And since we know from the observations that they seem to contain dark matter, only way out is that this whole dark matter effect is to be explained by a modified gravity approach, which then implies major changes to our understanding of gravity in the universe, and also kind of questions other things in cosmology, which, as I said, work really well within the dark matter model. So that's why, yeah, we're not really willing to go all the way yet, at least not as in astronomy as a whole field. There are some subsections, of course, which are willing to do this and are working on these modified gravity approaches as well. But yeah, we don't really know what the answer is in the end. So with that, I'm at the end of my talk, and yeah, thank you very much for your attention. I hope this was enjoyable.
Thank you very much, Dr. Pawlowski. That was an excellent talk. I enjoyed it very much, and you could see praise coming off your way in the attendees list and the chat. Thank you very much. And for those of you who do not, who just tuned in, Dr. Pawlowski is joining us from Germany right now, which should be there 5 o'clock in the morning. He joined us 4 a.m. Actually, we very much appreciate it. I myself in ISS as experiencing the sunlight here. That's interesting. So now let's go to the questions. And so the Q&A is open. Please send us your question. I'm going to start with a couple of questions I have. First of all, you didn't mention how well the modified gravity matches your findings. Is that like more than 90% or?
Yeah, that's a really good question. One of the problems with this modified gravity approach is it is, in a sense, more complicated. So you can't run these cosmological simulations they've shown in the beginning as easily because the model was developed to explain disk galaxies, rotating disk galaxies. And it works a lot better than just explaining this, but we don't have a whole cosmological model. So we don't have a good prediction of where should these satellite galaxies be that formed early on in the universe. So what you can do is look at the specific collision of two galaxies in this model, and then you see that this nicely explains the structures. But whether that really works out if you have the whole universe as a context, we still don't know. That's also one of the reasons why I'm reluctant to say, okay, this is definitely proof of this modified gravity approach. It's just one of the more exciting alternatives and some motivation to work in these directions as well. But yeah, I wouldn't bet huge amounts of money on either of those yet.
So besides dark matter and modified gravity, do we have any other likely explanations yet, or that's to be developed?
So there are a few ideas. So one is related to what we saw in the animation of this formation of a Milky Way-like galaxy. There are these filaments, right? So there's this cosmic web, and there might be a preference for satellite, or there definitely is a preference for satellite galaxies to fall in along those. Doesn't seem to be a sufficiently strong effect to explain what we see, but yeah, maybe there's a way to boost this. Maybe in a sense, our local universe might be special, that there's only one of those big filaments coming in, and then there's a lot more order than in a typical Milky Way-like galaxy. So yeah, we have to figure that out.
And besides your study of dwarf galaxies, are there any other observations that lean us more toward the modified gravity resolution other than besides the dark matter?
Yeah, I mean, there is a relatively well-developed model of modified gravity, which is called MOND, where it's just modified Newtonian dynamics, it's called, which makes actual predictions. So in MOND, you can look at say an image of a galaxy. You measure how many stars and how much gas there is, and then you can use just that to calculate how fast it should rotate. And that you do without any measurement of the rotation speed. So you make this prediction, and then you observe the rotation. And for all the galaxies you've essentially done this for yet, it always matches really nicely, which is something you can't do in the dark matter model. In dark matter, you always have the freedom to add as much dark matter as you want to match the rotation curve, but you can't make this prediction. If you just look at the galaxy, you don't really know how much dark matter there is. It might be kind of the typical amount, and then you have a prediction for some typical rotation curve, but you always have the freedom to shift it around. So in a sense, in a philosophical way, it's really nice to have a model which makes actual predictions, because that way it's testable. And there are a number of other predictions of this MOND model which can be tested and really match well on the scales of galaxy dynamics. The problem is, on the scales of cosmology, dark matter is much more successful, and you can make actual predictions there. So you have two models which in different regimes work really nicely, also make predictions that can be tested and confirmed, and are not really saying much about the each other's regime. So it is also a matter of perspective. If you're working more on galaxies and dynamics, you might lean more towards the modified gravity approach. If you work on cosmology and large scale structures in a very early universe, you basically say that's crazy talk, right? Yeah, it's interesting. I always like to kind of find compromises. So there are a few models which kind of try to combine the two. So you might have some kind of exotic dark matter which kind of mimics this modified gravity approach on the scale of galaxies. So you might combine it. So there are lots of exciting possibilities.
Okay, excellent. Thank you very much. And there are some questions. I'm merging a few questions here. So in the modified gravity model, can you explain a little bit more on what is modified compared to what we have in Newton's gravity?
So it's in a sense the strength of the gravitational acceleration in the low acceleration regime. So what does that mean? So on Earth, if you sit here, you have a certain weight, right, and you're attracted by Earth, and that is kind of very strong acceleration. So a lot of force on compared to typical astronomical scales. Even the solar system, the attraction of the planets towards the sun is really strong. If you go to a black hole, it's even stronger, of course. So it's really extreme. But the opposite end, if you go to a galaxy, you have a star moving around a galaxy at hundreds of thousands of light years distance from the center of the galaxy. The force this star feels is really, really small. And in Mond, you say that, yeah, it's really small, but it's a bit higher than you expect for just normal Newtonian gravity. So as soon as you kind of drop below a certain acceleration, the drop-off isn't as strong anymore as we experience on Earth. We can kind of get away with postulating that because this regime is not tested. We cannot do experiments on that in that regime, mostly because, well, we would do them on Earth, and then we have some gravity and acceleration. We can do them in the Earth orbit, or we would still feel the acceleration by the Earth and the Sun and the Milky Way center. So we don't really have a way to do a lab experiment to test this. But yeah, that's kind of the idea behind it. And then of course there are mathematical formulations for that. And, we are still working on kind of well, I don't, but people are still working on a relativistic version of that. So we, of course, Newtonian gravity is not the final word. We know that Einstein and his general relativity is kind of much closer, and that's really well-tested theory of gravity as well, right? So that really kind of was a modification in the regime of high accelerations. So with that, you can make predictions for black holes and regions around them, for example. Whereas now Mond would be a modification on the other end. So it's possible, it's not guaranteed that it works.
Thank you. And so in terms of the collision of galaxies, so is modified gravity explaining that better, or the Einstein's gravity?
Well, we don't really know which one explains it better, but they definitely make different predictions. So if you have the dark matter model and you collide two galaxies, you have these big clouds of dark matter around them, and they are interacting as well. They are basically sucking energy out of this encounter because you also have to shift around the dark matter. And that leads to kind of an in-spiral of these two galaxies, and they will merge relatively quickly. So there's kind of a friction of this dark matter on each other, called dynamical friction. So in the dark matter model, we predict that galaxies merge together more quickly, and this should happen more often. Whereas in the modified gravity approach, you don't have this dark matter around the galaxies, so the interaction would take a lot longer. So that's one of the predictions. And then the tidal tails you see being thrown out of the host, they would be much more extended in the modified gravity approach. So if you look at a specific system, a specific interacting pair of galaxies, you can usually find kind of matches for both of them so far, but nobody has looked at that in a statistical sense yet. So it would kind of result in different assumptions and initial conditions, and whether they are then consistent with the overall understanding of the model is a different question.
Okay, thank you. And also at the very towards the end, you showed a simulation of all those merging galaxies, and you mentioned that a single simulation matched a lot of observations. Is that just a coincidence, or did the people fine tune or change the parameters as it was progressing? Aren't we expecting that different galaxies have different masses, so they should be different?
Yes. I mean, it's of course the pictures were picked to match the simulation in a sense, right? But it's kind of showing a typical galaxy interaction. So of course, not each galaxy in the images will have the same mass as the simulation, but the overall features are the same, right? I mean, the matches were not perfect either, right? But the way that you have two galaxies which are more or less perpendicular to each other and they collide and you form a long tidal tail and you have these arcs, that's something which happens in a range of mass scales, of course. So you can always kind of find a match. So the geometry of the systems, I would say it reproduces the geometry of the system. It doesn't necessarily reproduce every feature. For that, you would try to look at one image and also get the velocities and kind of try to match everything, which is of course a lot of work because you have to run a lot of simulations. But yeah, you usually can do that. But this is really just an illustration more. Yeah.
Okay, excellent. And on the image that you had for your work, which had the contour of the these dwarf galaxies of the Milky Way, did I get correctly that the center of the Milky Way galaxy is in the Sagittarius, and was it off the plane that we see? Did I get that correctly, or?
Let me just show that again. Second.
Okay.
All right, here we go. So you are talking about this plot, I think.
Yes, here.
Yeah.
So is that the center of the Milky Way at Sagittarius?
Yes, exactly. Yeah.
Oh.
So this is the center of the Milky Way, and Sagittarius sits behind this. Behind the center.
Okay, so that's the dwarf galaxy behind the Milky Way. Am I getting correct?
Yes.
Okay.
Yes, that's correct. So the center of the Milky Way is what we call about 8 kiloparsecs away, and Sagittarius is about 3 times further away. So it's kind of sitting on the other side of the Milky Way, and the plane of satellite galaxies. So the structure of satellite galaxies is kind of in between, right? So it means that it is kind of perpendicular to the direction towards the center of the Milky Way. That means that Sagittarius is kind of also outside of this structure. So it can't, there's no way geometrically that it takes part in this coherent rotation. It's kind of one of the definite outliers from this.
Okay, and
but yeah,
is that the biggest dwarf galaxy around the Milky Way?
No, so the Large Magellanic Cloud, the LMC here, that's the biggest dwarf galaxy around the Milky Way, followed by the Small Magellanic Cloud. So these two are really, really huge. It's billions of stars each, and they have gas, which they are losing in this stream here, which is kind of following them around the Milky Way. And then there are a few other, Fornax, for example, I've shown, which is also really massive. Fornax is, should know where Fornax is. It's one of these down here. I think this one. And yeah, so Sculpture, Draco, the Leo 1 up here, these are also relatively massive, but not nearly as massive as the Large Magellanic Cloud.
Okay. And so what about the you mentioned the mass, and then what about the area that they cover, the volume? Is Sagittarius more voluminous than that, or am I seeing that wrong in the
well,
image?
yeah, that's the interesting thing about Sagittarius. As you see, there are these contours here, right, which kind of go north and south. So Sagittarius is so close to the Milky Way that it's currently being ripped apart. So it's similar to this tidal feature, just that it's involving two galaxies of very different mass. So you have the Milky Way, which is really big, and then you have Sagittarius, which is a lot smaller. But it's being ripped apart, and it has stars spread essentially all over the sky. So in a sense, it is much more voluminous. It's just that these stars don't really belong to the galaxy anymore because galaxy lost them. It's being torn apart right now. So there's a core here which is still bound, but yeah, with time it moves around the Milky Way and it just loses the stars, and then at some point it will just be gone and just be a stream of stars around the Milky Way.
Thank you. And talking about the stuff that's around the Milky Way, is there a clear and generally recognized definition of what distinguishes between a star cluster and a dwarf galaxy?
Excellent question. This is a really good question. Because it's a matter of definition in a sense. So one common definition is it's a galaxy if it contains dark matter, and it's a star cluster if it doesn't. But there are now galaxies which have less stars than star clusters, and star clusters which are more massive than galaxies. And it's a blurry line. And also, of course, the problem with this definition would be that if it assumes that there's dark matter, right? If there's something like modified gravity, then there wouldn't be a difference in this definition anymore. At some point, star clusters look like they have dark matter, and in other cases, they wouldn't. So it's not really clear. The other way of defining it is maybe more convincing for me is their star formation history. So star clusters usually form in one event or in a short series of events. So they have stars which are more or less of the same age, whereas galaxies typically evolve over billions of years. So they would have a range of stellar ages, and that's somewhat more difficult to identify. But I think that's the better way of discriminating these two.
Thank you. And some people like to miss the reason that you mentioned why tidal dwarf galaxies should be free of dark matter. Can you explain that more?
Sure.
And
yeah, it's so as two galaxies collide, you need, in a sense, the disky material in a disk galaxy to form these long tidal tails. So that's because you have the disk spinning, and then you have in a sense, the orbit of the interaction. And if these two align, you get strong forces ripping this material out. Now, if you look at the dark matter component, it's kind of we call it dispersion dominated. So it's really just random motions of particles, and that is not aligned with the spinning of the disk. So there's, in a sense, less velocity to add to the dark matter particles, and then they don't participate in the formation of this tidal tail. So the tidal tail is independent of the dark matter. So it's in a way, it's these interactions separate out the stellar and gaseous component from the dark matter component. And so only the stellar and gaseous component is available to form these structures. And these structures are so small, it's just dwarf galaxies with which do not have a lot of gravitational potential. So they can't even attract the dark matter, because the dark matter particles themselves from the big galaxy are zipping around so fast that they would just fly through the little dwarf without noticing. So that's why you kind of would just form these dark matter free objects.
Thank you. So you mentioned about the scale at which the dark matter works, but can dark matter have a say in formation of solar systems, planets, and stars?
Again, the issue there is it's moving too fast. So for these little tiny scales, it doesn't really contribute because structures don't form on these little scales. I mean, there are possibilities that you form really, really small clumps of dark matter, but they would still be sufficiently diffuse. So the size would still be big enough compared to a planet that it doesn't really make much of a difference. At least if you take the standard so-called cold dark matter approach, or even others. So if you just have a really simple model of dark matter, there are ideas that dark matter might be a mix of different kinds of particles, and that some of them might also form kind of little condensations and maybe little stars of dark matter. So there are a lot of ideas, which is also kind of a sign that we don't really know that much yet. There are a lot of possibilities which we are all testing, but it looks like it's definitely not necessary for dark matter to have any impact on the formation of stars and planets. So in a sense, yeah, we can explain most of that without needing dark matter, which is also nice. So some parts of astronomy are relatively safe from whether there's dark matter or not.
Okay, thank you. And again, we need some more explanation. Then for the next question, we need some more explanation on why the dark matter theory predicts that these satellite galaxies be random. Because for our understanding, the solar system forms in a plane, the galaxy we expect to form in a game. And can you explain more, again, more?
Yeah.
You need to explain a little bit, but explain more why.
Yeah, sure. I mean, it is, again, related to also the tidal dwarf galaxy issue. So again, it's because these antiparticles, by definition, don't interact with others. They don't exchange energy that efficiently. So they cannot cool. So when you have a gas, so when you form a galaxy or you form a planetary system, you essentially have a gas cloud which cools down. And as it cools down, it becomes more compact and collapses, and then it has some spin, some angular momentum. And that will, in the end, because it cools, but this angular momentum is conserved, it will form into a disk. So this cannot happen with the dark matter because it cannot cool. So the dark matter particles cannot become slower and they cannot really collapse. So that's why you have these little disk galaxies in the centers of big dark matter clouds. And that's also why these tidal dwarfs don't form out of dark matter, because the dark matter is just too fast and has these random velocities. And similarly for the satellite galaxies, then they are basically just big blobs of dark matter. So the potential in the gravity of these galaxies, the mass budget, is completely dominated by the dark matter. Some dwarf galaxies look like they have 1,000 times more dark matter than luminous matter. So it's really just the dark matter which dominates where they are and how they move. It doesn't really make a difference whether there's a star inside or not in the cosmological model that's based on dark matter, of course.
Thank you. And now, can you explain a little bit about the origin of these dwarf galaxies? Are they all formed in the mergers, or could they be like captured galaxies in a satellite? What are the possibilities?
Well, yeah, the possibilities are they are these old building blocks of galaxies. So in the standard model of cosmology, you form these little galaxies first, and then they merge together. So many small ones form a big one, but then the process is never really ending. So there would be still little debris around the Milky Way, which are in the process of merging with it. And that would be the satellite galaxies. So those would be the dark matter dominated ones. And then, yeah, of course, you also have where we know that we form these tidal dwarf galaxies as well. We see that in the universe. The question is, how often does it happen? Is it sufficient to explain it, which I personally doubt. But yeah, you would have those as well. For a given galaxy, it's hard to kind of decide. If you see that it is still embedded in a tidal tail and it's really young and it's forming stars together with a few other ones, you can really safely say this is probably a tidal dwarf galaxy. If you insist that we work in the dark matter model, you can look at a given galaxy and say, okay, if this is looking like it has dark matter, it cannot be a tidal dwarf galaxy. But that's kind of a circular argument because it's based on your assumption. If there's modified gravity, it would still look like it has dark matter, but it doesn't. So it's at some point it's really difficult to kind of disentangle these two. But that's the two main possibilities.
Thank you. And what's the latest count on the number of dwarf galaxies for the Milky Way? You're discovering more and more, right? Still.
Yeah, I mean, people are discovering that. It's not actually my work, of course, but it's about 60. I say about because we don't have confirmations for all of them, and there's this issue of is it a star cluster or a galaxy? For some of them, they are really at the borderline. For a long time, it was really clear just from how big they are and how massive they are. Okay, this is a star cluster, this is a galaxy. But as we get to fainter and fainter systems, if you only have 1,000 stars, we would classically call it a star cluster, but then they move so fast that they seem to contain dark matter, and suddenly it's a galaxy. So yeah, around 60.
Excellent. And then comes the question of how do we recognize if something is a dwarf galaxy of Milky Way? Is it just the redshift and the distance that determines it, or do we have other means to find out?
Yeah, I mean the
gravitational
distance. The distance is the main thing. So if it's within a certain distance of the Milky Way, so if it's much closer to the Milky Way than anything else, it's usually assumed to be a satellite of the Milky Way. Of course, the velocity also plays into that. If it's really, really fast, it might just be flying by. There's this kind of, it's termed backsplash galaxies. So they kind of fall into the Milky Way, but then they zip out again because they're too fast, and then they might fall back at some point. But yeah, it's really just the distance, and this distance we luckily can measure relatively safely. For external galaxies like Centaurus A, it gets a bit more complicated. Centaurus A is still close enough, but we always have an uncertainty on the distance measurement. So if it's a really far away galaxy and we measure the distance of the satellite galaxy, usually the uncertainties are bigger than the sphere of influence of the host. So then kind of have to make probabilistic arguments. How likely is it to be a satellite? And if there's nothing in front or behind, then it's usually safe bet that it's a satellite. But yeah, doesn't get easier the further out you go.
Thank you. And can you explain again and more about how do we measure the apparent motion of the dwarf galaxies?
Yeah, it is relatively simple conceptually. You take a picture, you wait a few years, you take another picture and see how far the stars have moved. The problem is the motions are really small. So if you take one of the best instruments for that is Hubble Space Telescope. High resolution, no disturbance by any atmosphere, really known systematics. We really know what the people doing this work really know what the system does. But even then, the motion of your stars over a few years in a satellite galaxy is usually a thousandth of a pixel. So a star is kind of a spread out blob spread over several pixels. And so you can measure the peak of that, and then you compare that from image to image, and you combine thousands of stars. That's the other benefit of Hubble, that it can go really deep. So in a sense, it measures a lot of stars in one go. And then you see how far did this move relative to a frame of reference, which is usually defined by background galaxies. So in any direction you look on the sky, you will always have some background galaxies. And those are so far away that they shouldn't move on the sky, right? So they are kind of fixed, and then relative to them, you can measure how fast the stars in this galaxy move. And by really, in a sense, just comparing where were they a few years before, where are they now? The good thing is patience kind of pays off here. Every time you get one of those proposals, those observing proposals rejected, you essentially gain another year and more precision. So your proposals get better and better with time by themselves. Problem is Hubble will not be around for that.
Okay, thank you. Let me see if I have this in perspective. So we have the foreground stars of the Milky Way, then we have the dwarf galaxy, and then we have the background galaxy.
Yes.
And so we can measure the motion here of the dwarf galaxy relative to these two things, right?
Yes, yes. You prefer to measure it to the background galaxies because they are basically fixed, but you can differentiate between the stars of the satellite galaxy and the foreground stars by their motion, right? So the foreground stars will follow the motion of the Milky Way disk, most likely. So they would have a different velocity than those of the satellite galaxy, and they will also be much faster. So that kind of separates them out in velocities.
Okay, so we have high resolution enough images of the dwarf galaxy that we could see all the individual stars.
Yes.
Okay. So
yeah. I mean that's what you need to do, and that's why it's so difficult to do that further away as well, right? So it's that you don't see enough stars anymore, and also if it's further away, the motion is so much smaller that you would have to wait tens of years to see anything. But yeah, the instruments get more and more precise as well. Like I said, the Gaia satellite, they just had another data release with even more precise information. So it's an exciting time for this kind of work.
Okay, excellent. Thank you very much. And now for the next question, how does this relatively new discovery of the great Laniakea and the great attractor come into play with this? is that large enough that it has nothing to do with the dwarf galaxies, or is there something that might be at play here?
Well, it doesn't really impact the distribution of satellite galaxies on the scale I'm looking at, but there is some connection to this larger scale structure. So if you look at the Centaur satellite galaxy plane, or the one around Andromeda, and compare that to how the galaxies are distributed and move around the local group on Andromeda itself, so on a somewhat larger scale, you actually see that they are aligned with the orientation of this cosmic web. So there's some connection there. So that might indicate that there's a preference for satellite galaxies to fall in along this cosmic web, and that might help explain the signal. It might also mean that two galaxies which interact preferentially, of course, fall in along the cosmic web, and then this is the preferred orientation of tidal debris or tidal dwarf galaxies. So in a sense, it works with both scenarios. So it doesn't really discriminate between the two, but it's nicely consistent with both of them, which is also good. But that's on somewhat smaller scales. And then if you go even further out, then of course these big structures emerge in the cosmology, and they might have an impact on the smaller scales, right? So they might kind of shape the orientation of these filaments, and that's why certain it's called constrained simulations, where you have cosmological simulations which don't just reproduce a random subset of a volume, but also actually try to reproduce features around the local group, like nearby galaxy clusters. That's where they are becoming important. And there's one set of those simulations developed in Potsdam, which we're working with as well. So there will be more nice results on that in the future, I'm sure.
Thank you. And then we are almost out of time here. We have a few more questions. Let me go over another thing here. So are you aware of somebody's, oh, you have some, is there somebody's, nice, maybe we should say hi to him. Yeah, excellent. Thank you very much for accommodating us. We will try to not disturb him more. So,
he was born in OC, so he's one of you.
Okay, I see. Excellent. Dealing with an American there. So somebody's wondering if the universe is about 14 billion years old, and as galaxies get older, we think that they lose their spiral shape and they become more bulgy. How is it that we still see a lot of spiral galaxies?
Well, they shouldn't really just become more bulgy by themselves. They are not like humans. At least that's what happens for me. So of course, the more they collide with each other, the more randomized the stars become, and so they form this random component of stars in the center usually, which is called a bulge. But at the same time, if you have two galaxies which collide, which still contain a reasonable amount of gas, they will relatively quickly reform a disk, and that would then kind of explain this. So there are, for example, suggestions that for Andromeda or nearest neighbor galaxy, there was such a collision of two major disk galaxies with a mass ratio of 1 to 3 or so a few billion years ago. And we know today, if you look at it, okay, it has this random bulgy component in the center, but it's also a really nice disk. And in those simulations, you can actually rebuild a disk because you have sufficient gas in the galaxies to do that. So yeah, it's not really surprising that you still see that. And cosmological simulations, these big simulations which start early on and then evolve galaxies and form them, you don't only simulate the dark matter nowadays, but also the gas and the stars, and you form disks. And for a long time, it was a problem that they couldn't really form these narrow, thin disk galaxies until today. But this has been overcome. So depending on the assumptions you put in your code, you can actually reproduce that. So it is possible, I think.
Thank you. And you also mentioned about the interaction of the dark matter. So it's not interacting and it's interacting only gravitationally. What about the self-interaction of dark matter? Can that factor into the simulations and observation, the difference between simulation and observation?
Well, what's at least in the simplest models, it's assumed that dark matter also interacts with itself only via gravity. So there's nothing else going on. So that makes it easy and simple to calculate, but then also it results in the fact that this shouldn't have any real features internally. The difference is that, yeah, if you switch on some self-interactions, then, well, there's so-called self-interacting dark matter. That would mean that it can exchange energy internally. That would change the distribution of dark matter in a galaxy, for example. So in the center, usually you get a strong peak of dark matter, very high density center. And that would, if there's more energy exchange, that could be smoothed out, for example. So you could get a core of more constant density and then falls off at some point. So there's a difference there. And then, of course, if you have even more exotic dark matter, you might have little dark matter atoms, and they might cool. And then there's what's called dark photons, which is kind of weird because photons should be light. So it's kind of dark light that is emitted by this dark matter. So there are these really exotic models, which then could lead to really formation of dark stars and the kind of a whole different set of objects in the dark sector, which we just don't know about because it doesn't interact with light. But yeah, these are kind of exotic and alternative ideas.
Thank you very much again for joining us this early. And so we are here at the end of the meeting. Again, thank you very much for answering all the questions also. So before ending this meeting, I would like to bring to everybody's attention the upcoming events from the OCA calendar available on our website. Next general meeting will be on February 12th. Dr. Brian Monachelli from JPL will be talking about exploring Martian geology. Beginners class will be on February 5th. And Ventura County Astronomical Society's general meeting will be held by OCA on January 15th next week. Open Spiral Bar will be tomorrow night. And finally, you can help us improve the quality of our meetings by answering the questionnaire, which should be already open in your browser window. With this, I would like to thank everybody for being with us and wish you a very prosperous year ahead. Thank you and good night.